Iowa State University, and he is deeply passionate about intersection of electrical engineering, optimization, statistics, and economics. His research and teaching focuses on modeling and optimization of modern energy systems, and he's currently involved in projects exploring hydrogen as a clean energy carrier and energy management in microgrids under uncertainty. So yeah, Diego is going to talk about green hydrogen economic model, a Colombian perspective, and we are so eager to hear your perspective.
Okay.
Diego,
Thank you so
the
much.
stage is yours.
Thank you so much, Jalad. Thanks for your assistance and for the people online to be here. And yeah, I'm coming from Colombia. This is my second time here at DTU, and the first time was in 2017 in one of the optimization summer schools organized by Jalai and his team. And we had a very good time here. We enjoyed a lot and we learned a lot. And yeah, and since that I also have DTU in my radar for research and everything. Yeah. So Colombia, maybe just to give you a little bit of context of Colombia in terms of energy. Colombia is a quite big country. We are more than 50 million people there. It's in the north part of South America. We are basically surrounded by two oceans, by the Pacific Ocean in the west side and the Atlantic Ocean in the north side. Colombia is energy matrix is mostly based on hydropower. We have around 13,000 megawatts of installed capacity of hydropower, and so it's mostly it's more than 60% of our generation, and the total installed capacity is around 20 gigawatts. Wind is increasing right now, but if you asked me maybe 3-4 years ago how much wind do we have, I would say maybe a very few megawatts. Now we have around 1.3 gigawatts. And I think, and the reason for that is because we are mostly renewable with the hydropower, and maybe didn't see the need for growing solar power and wind power that fast. But of course, it's important to diversify the energy portfolio. And actually, currently, Colombia is trying to install around 9 gigawatts of offshore wind in this part of the ocean, the northern part, via CFD contracts for differences. And so that's the plan for around 2030. And Colombia also has a hydrogen roadmap. Colombia is seen like a country with a strong potential for hydrogen production. In Colombia, we created a roadmap in the country, and where we want to have a $1.7 per kilogram price for hydrogen. That's like the goal for 2030. And basically, this could be achieved by having a massive production of green power of solar power in the north part, and that power here in this area, in the very north part of Colombia, we have a strong wind potential and also solar power potential. And with all of that energy, we plan to build like a hub for hydrogen, produce green hydrogen over there. And we also have another possibility to have another hub here in Cartagena, Cartagena has also a port. So they have these places have like a mixture of conditions that could make Colombia a good country for exporting hydrogen. And okay, I think that's a little bit of context for this. And this I wanted to I say to Jalal that I could tell here to you. I could speak about a project we have been involved the last 2 years. But my main area of work is mostly focused on not on the technical part of the electrolyzers, but on the market side. So that's why I contacted Jalal for coming here and talking to you about this. Okay, see this basically what we are investigating here is like we are trying to find the optimistic conditions or the conditions, market conditions and energy policy conditions that would be required to have a hydrogen production price of 1.7 as the roadmap suggests for Colombia. So we are like comparing two business models that would allow us to see which of them is more convenient for Colombia and which of them is the easiest to get to. Okay, so we started from this. We know that according to previous literature, we have seen that hydrogen has been produced by renewable power or also by the power grid, but this power or this electricity is used for feeding the electrolyzers, but there is no like a strategic production or management of the electricity, and then all of this hydrogen is sold to the hydrogen market. So now we started also to see different structures where there is like a mixture of or a strategic production where we have electrolyzers, where we have renewable energy, and then we start to make decisions about selling power directly to the grid, or if the price of hydrogen is very good, we can decide to produce hydrogen and sell it to the hydrogen market. So there is like a hybrid, let's say, business model where not only the business model is to produce hydrogen and sell hydrogen, but also to produce electricity and sell electricity. These are very interesting references. We have also been studying closely to the people or the students and work of Professor Reichenstein from Stanford University, and also some important work developed here at DTU. I think Baumhof this is a reference from DTU, maybe one of your students here. And this is what we are trying to do here. And we will analyze two business models. In our case, we have electrolyzer, we have a hydrogen market here, and we also have the first one we are going to analyze is assuming that the electrolyzer is going to be fed only by solar PV project, and this hydrogen is going to be sold to the hydrogen market. We also need the water. We will consider a little bit of cost of water, and some part when the electrolyzer cannot work, we will sell power or electricity to the grid. And the other business model is we are going to consider is the case where we are, it's like a self-generation model, And then we have also the electrolyzer always fed by the grid, and we produce hydrogen only when hydrogen price is attractive. I will explain that with in detail later. Okay, so this in order to do this, we will analyze. We will focus on the size of the electrolyzer. We will find optimal sizes of the electrolyzer in order to achieve very competitive prices for hydrogen in the Colombian context. So we will parameterize the size of the electrolyzer with a parameter, we call it phi, and phi represents the ratio of the hydrogen, of the electrolyzer capacity to the solar power system capacity. So phi, a small phi, means that we have a very small electrolyzer compared to the solar project, and a large phi implies that we have a very large electrolyzer compared to the solar power system. So that's I explain phi because we will see it in some of the slides. Okay. Now, in the first case where we have the electrolyzer directly fed by the solar system, we are considering the not many technical details, but we do use the three-state model that is proposed or is implemented or analyzed in this reference. I think this is from DTU. And we are considering the on state, the standby state, and the off state. And then we are doing, since we have lots of solar power data in Colombia, in our university, we are using 1 minute data for 3 years. So we have this level of detail for the solar production, and then we will see for how long the electrolyzer can produce hydrogen and for how long the electrolyzer needs to be at the standby state, for instance, and for how long the electrolyzer will stay in the off state. So we will consider that the electrolyzer will produce hydrogen when solar power is above this percentage of the electrolyzer capacity, which is 50%, and the total capacity of the electrolyzer. When solar production is in this range, the electrolyzer, we will consider we can produce hydrogen. When solar power is above the electrolyzer capacity, we will sell this extra power to the grid, and this when the solar power is below this percentage of electrolyzer capacity, the electrolyzer is going to be in standby, and we can also sell this electricity, the yellow area, to the grid. So the yellow means electricity sales, and the green means hydrogen production. It's not here, not in this part, because in this part we will be during the.
Yeah, but is it the kind of optimization, or it's got that rule?
It's ad hoc. That's ad hoc. It's not optimized. It's not optimized. Okay. Actually, this is quite difficult to implement because we will need also a battery for, the degradation issues for the electrolyzer. Have been not considered here, but just for we will compare this to another business model which is more more promising. So I'm not gonna focus on too many details of this, but what I just explained in the figure is this curve of Q is hydrogen production, and basically the red one shows the production when the electrolyzer is smaller in terms of capacity than the solar system, And the blue one is the production when the electrolyzer is bigger than the solar system. The only difference is here the saturation when the solar system is smaller. I mean, when the solar system is bigger than the electrolyzer, of course, we cannot produce more hydrogen than the capacity of the electrolyzer, of course. And this area is the conversion factor that allows me to have to convert from power to hydrogen, right? Okay. In this range, we are not producing because when solar production is very small, we cannot produce any hydrogen. Okay. So electricity sales is basically this area is a difference between the total energy, the solar energy, and the production of hydrogen. So that difference gives us the energy that is going to be sold in the market. We also have a standby electricity consumption, that is going to be present when solar power is below this 50% of the electrolyzer capacity, and the standby electricity consumption, according to reference, is around 40%. This rho zero factor is around 44%. I'm sorry, 4%, 0.04 times the electrolyzer capacity.
Diego, sorry, I have a question. So about the size of PV and electrolyzer, is it something that optimized or not?
Yeah, we will optimize it. We will see what would be the final effect of the fee term in terms of the financial indicators or financial parameters.
Also the dynamics of PV production, like Markov chain kind of simulations to see what the optimal size of electrolyzer should be?
Yeah. I'm not gonna show the total simulations because I don't have it here, but we are doing all of the statistical analysis. We are doing with this. We have I will show you some of distributions of the solar production, and I will also show you some distribution of the electricity price. So historical electricity prices in Colombia and the solar production that we have in the rooftops of the building of our university.
Are connected to transmission level, I suppose.
No, they are not at the transmission level. They are at the distribution level. Yeah. Okay, so we are start working with expectations, the expected revenues. The revenues of this business model are the revenues of selling hydrogen and the revenues of selling electricity. All of this in terms of the size, fees like the relative size of the electrolyzer. Okay, we do all of these terms expectations, and for the we are comparing or analyzing different technologies of electrolyzer. We have investment costs, we have fixed operational and maintenance costs, we have the cost of water. Oh no, I'm sorry, this is the variable cost of the electrolyzer. This is the efficiency of the electrolyzer, the kilowatt hour required to produce 1 kilogram of hydrogen, and these are the hours of lifetime of the electrolyzers. For the economic evaluation, we are also considering that the owner of this kind of system, we have tax obligations in Colombia. For the corporate tax rate is 33%. It's quite high, I think. Yeah. Here is
for production. Do we know the production tax?
The tax. This is the rent tax, the income tax. Okay. We have the Colombian government has promulgated different tax incentives for non-conventional renewable energy and also for hydrogen. And the incentives provide 50% of income deduction, 50% annually, and the total can be up to the 50% of the capex of the system. So it's like the half of the investment can be deducted from annual rent, right? Also, the depreciation rate is allowed to be 33%. Without the incentive is 10%. So this has also an important effect over the final results. Okay. So this is an example of the actual data of solar production. We convert the data to like we per unitize the data. Let's call it that way. We have our rooftop solar system is around 10 kilowatts, but what we did was we collected the data, 2 years of data, and we divided the data by the 10 kilowatt in order to have a unit production or the production per kilowatt, right? And then we construct different distributions for 15-minute periods. So we have for 1 hour we have four periods or 4 15-minute periods, and we have two years of data, 1 minute data. So in this case, I'm showing the data or the distribution for the period between 2 p.m. and 2:15 p.m. During 2 years, and the distribution looks like this. You know, the histogram shows the empirical distribution of the data, and we have two modes, let's say. And that's because we have 2 years and we combine. We have in Colombia we don't have seasons like here, but what we do have is 2 periods of rain and 2 periods of summer, let's say that way. Yeah, and per year. So we have 2 summers in a year and 2 winters in a year, let's call it that way. And so that's why we have like 2 different histograms, but this is actually the one distribution for this period. So what we did here, in order to come up with, instead of having simulations, we constructed.
And what is the blue circle? The dark blue circle.
Oh, this is because we were trying. Okay, what we did, we fitted this bimodal distribution using a polynomial distribution, and we did it using an optimization problem. What we did was to minimize the maximum distance between the empirical CDF and the theoretical CDF, right? So we were focusing on that, and basically we did this. We tried to come up with a polynomial PDF. It's parameterized by parameters theta. Okay, this is very generic, but we are doing a polynomial with, I don't recall at this moment the degree of the polynomial, but basically what we have is a proposal of a generic polynomial here, and then we minimize this maximum distance, which is the distance between the 2 CDFs, as I mentioned before. And the constraints of this optimization problem are the whatever PDF we come up with needs to be positive, of course, for all of these terms nu, represents the unit solar production per unit, and this is the it says that, of course, that the area below the curve of the PDF has to be 1. So basically, what was this? And this is this curve, this polynomial PDF is one example of the results for this period. And we did that for all of the periods between 6 p.m. and 6 a.m. and 6 p.m. because we don't have sun in other.
So why do you try to fit a distribution? Why not using samples directly?
Yeah, that's a good question, because we could. I'm sorry, I'm going back. In all of these expressions, when we see the PDF of the solar power, we could obtain expressions.
You want analytical solutions?
Yeah, we did we computed expressions for this. I don't have them here, but we could come up with expressions. Even with these strange integrals, but they are not that strange. They are basically 0 in some of the intervals, and they are solvable for other intervals.
How about at the high end, so at the 1.0, is that real that it goes up the PDF?
Yeah, no, that's, I mean, it's like when, yeah, this, we couldn't control this, of course, because we basically, what we are controlling is this distance, this like a step function that we are showing here, the empirical, and the red one, that's the polynomial CDF. So basically, just for the result shows this, but this doesn't add a lot of probability, because that's what matters in the end. This area here, in terms of probability, is very similar to the green one. So that's what we have here with the red polynomial. The red polynomial is the area, the accumulated area below the curve of this polynomial PDF. So yeah, this is, it shows a strange behavior in the final part close to 1, but the area that is here is very similar to the area that is here. That's what we need most of the time, because we are doing the integration of that function. Okay, for electricity prices, we have this. We analyzed electricity prices in Colombia. We have a stock market as well for not maybe 30% of the generation in Colombia is sold in the market, and the other 70% is sold via contracts, bilateral contracts. So
the empirical part, is that the real data?
Yeah.
Okay.
Yeah, the real data. Yeah. So these are the prices for electricity from 2021 to 2023. These are basically the typical numbers in Colombia, and these prices in Colombia are mostly affected by meteorological conditions. When we have a long summer, sometimes that happens, the Niño phenomenon. When the Niño phenomenon occurs, some hydropower producers, they take advantage of that, and they submit the high prices, and then we have these kind of things. But even when the price is, the stock price is very high, we have a capacity market that protects the customers or the households, and we pay, we call it a scarcity price. That is a cap on the price, and so in order to not to pay the actual stock price when the Niño phenomenon is present. Okay.
And you did the same optimization to fit the distribution?
But for electricity prices, we are fitting. We did it, but we prefer to employ a well-known distribution, but we use we didn't say here in the slide, but we use the Kolmogorov-Smirnov test in order to see which distribution fits the best, the prices.
So all the green ones should add up to 1, 2.
Yeah, there
Seems to be a factor 10. Not. So
which one? This one?
So you have 0.0.
The y-axis.
Yeah, the y-axis, the left y-axis is like 0.02. 0.0.
Yeah, but this is density. Yeah, so the integral over this one, the green one, it has to be 1, right? So that's
so it's only 0.1%. You should add up. So roughly, I think that's a 0 or factor 10.
okay. If we are okay, I need to check maybe the scale, but
the integral doesn't look like 1. That's
what he's saying. Yeah. I need to check the scale of the y-axis maybe, but yeah, but the numbers, I mean, the numbers are okay in the sense that we fitted these distributions. We also employ different distributions instead of, apart from gamma, or different, but the gamma was the one that was selected by the Smirnov Kolmogorov-Smirnov test. But maybe I need to check the scale of the y-axis to see if there is a mistake over there in the scale. But just for the display. But okay, and okay, these are some results of this case. We have here the production, the expected production of hydrogen per year in tons, and for different technologies. Different technologies have different efficiencies, and we evaluated the production for different sizing of the electrolyzer, and we obtained that, for instance, maximum production can be achieved when the electrolyzer is 0.971 times the solar capacity system, the capacity of the solar system. And we also have here how electricity sales change when the relative size changes. When we have this one, in this case, when phi is 0.971, we maximize the production of hydrogen, but at the same time we minimize the sales of electricity, because in this business model we are either producing hydrogen or selling electricity. So that's why we have that here. So, but we are not proposing choosing phi based on these plots, but what we have to do is to analyze the entire financial behavior of the system. Basically, we are doing here finding the expected value of the net present value, which is the expectation of the cash flow, which is the minus capex. And these are the discounted values of profits, and we call the taxes. So, and I'm not going to the details of this, but the cash flow contains, these profits contains revenues from sales, electricity and hydrogen, and the cost of the system, and taxes I explained before of the numbers related to that. we are considering two important metrics. That one is the LCOH. It's very well known. Is the levelized cost of hydrogen. Is the price such that the net present value of the hybrid system is zero? So assuming that we have the NPV function, this NPV function depends on the price of hydrogen and the relative size of the electrolyzer. In this case, when we find the price of hydrogen such that this NPV function is zero, we call that the LCOH. And of course, depends on phi, because that's what we are analyzing here. We are analyzing the effect of the relative size. And that's a very well-known metric and a very important metric, but we also study what Professor Reichenstein has called the break-even price of hydrogen. And this break-even price is at the price at which hydrogen starts to add value to the solar system. So, and it's very interesting, the relations between these two, and I will show you in a minute what's the big difference between them. And this price, we can compute it as the price, the hydrogen price at which we achieve the same price of the solar system, assuming there is no electrolyzer at all. So it's the price at which it's profitable to also produce hydrogen. If the price is below this price, if hydrogen price falls below the break-even price, it means that the hydrogen can be, the system itself, the hybrid system could be profitable, but the hydrogen is subtracting value to the entire system.
Earlier, you said Colombian target is $1.6 per kilogram hydrogen.
Yeah, for the LCOH.
But is it about BEHP?
No, that's the 1.7 is the LCOH for Colombia. They just say we want hydrogen production price to be at most 1.7. So, and we consider that as the LCOH. The break-even price, of course, depends.
Lower than 1.6. Otherwise, hydrogen projects are not profitable. It should be like 1.2.
The break-even prices are they have to be actually greater in order to, sometimes I will go to this slide, maybe to make it clearer. This figure shows the size of the electrolyzer in the x-axis, and in the y-axis, I'm showing the hydrogen price. And there are some regions here, and these regions are classified according to the net present value of the hybrid system. And this line of the LCOH shows the LCOH according for each sizing of the electrolyzer. And it says, for instance, that if I have an electrolyzer of half the capacity of the solar system, we will need a hydrogen price around $5 per kilogram. But if I have a price below that, so it means that the entire hybrid system will fail because the NPV is always negative. But there is a region in between. This blue line means plots the break-even prices, and it means that in this region, in between LCOH and BEHP, means that even though the NPV is positive of the hybrid system, the H2 system extracts value. Means extracts because the NPV in these cases with the hydrogen production is below than the NPV of the system just selling power. So it means that in this case, it's better to keep producing, keep selling the electricity and not use the electricity to produce hydrogen. But in this area, in the green one, what this says is that in this combination of sizes and prices, hydrogen prices, in this area, it's worth to produce hydrogen as well. So that's basically the meaning here. And this happens is because we have a dilemma when we have the electricity from the solar PV, and then we say, okay, and the dilemma here was, you asked me at the beginning if we were optimizing the strategy, and I say no, it's ad hoc. So basically, the policy here is produce if there is enough solar power for starting or for running the electrolyzer, produce hydrogen. Otherwise, don't do it.
Okay, maybe it's for later, but in my head, VHP includes LCOH plus opportunity cost of not selling power in the electricity market. So the difference, discrepancy maybe reflects opportunity cost.
Okay. That's a good way to call it. Yeah, this is opportunity cost, this difference between the two. So this kind of picture gives us like an entire understanding of what should be the size of the electrolyzer, what should be the price of the hydrogen market in order to analyze if it's profitable or not to have a system like this. I'm going to show you the second business model where we have a self-generation system, and we are going to produce hydrogen, but not using directly the solar power. Okay, but not using the solar power, but we are using just the electricity, and then we will use the following rule. Basically, we will produce hydrogen if the marginal revenue of producing hydrogen is greater than its marginal cost. Basically, we have these terms. I will just explain them here very quickly. The first term is the revenue of selling hydrogen, and the other three terms are the electricity cost for starting the electrolyzer, the water cost for the electrolyzer, and the replacement cost of the electrolyzer. We are also considering the replacement cost, assuming that for each kilogram that we produce, we need to, basically, we are dividing the capex between the total number of kilograms that should be produced with the electrolyzer in order to have like a measure of how much is each kilogram of the electrolyzer. So basically, this rule, when this rule happens, it means that when the hydrogen price is high enough to cover this cost, we can produce hydrogen. This we call this term the production value of hydrogen, and without the electricity part, all of the hydrogen terms we call the production value of hydrogen. And basically, we produce hydrogen whenever the production value of hydrogen is greater than the electricity price. So that's.
But Diego, if you are maximizing profit, that constraint will be hoped. Why we need to enforce it explicitly? I mean, we are not gonna.
I mean, this is for in terms of operation. So it's like in everyday operation, we have T implies periods. So it means that in this period, at this moment, are we producing hydrogen or not? And then we compare it to if our production value is.
Yeah, I see. But if you are maximizing, if you saw an optimization for profit maximization, that will happen. We don't need to enforce it explicitly.
Yeah, that's true. Yeah, that's true. Yeah, we want to, in this case, we want to compare this kind of rules. These kind of rules have been employed by other people. Like I mentioned, this work by Professor Reichenstein from Stanford. They use as quite similar rule for wind. We are doing some other modifications in order to evaluate the sizing and evaluate the hydrogen price. So we want to evaluate how the sizing impacts this. So I don't know if it would be possible to use an optimization model for maximizing profits, and where the sizing could be a decision variable as well. Maybe I need to write it down and see if we can do it. But thanks for the suggestion. Okay, I'm going to skip this because it's pretty much the same thing as I mentioned before. But this is the final result for the second case. In the second case, we are also analyzing the impact of the sizing in terms of prices. And what we have found here, maybe I didn't mention the values of the break-even prices, but in this case, the break-even prices are much lower than the first case, are lower than $4 per kilogram, and these are the LCOH values for this case. And of course, this policy says that we have some level curves of the NPV. These numbers reflect NPV values and net present values. And this shows that in this business model, basically, the greater the electrolyzer, the better for this situation, as long as the price of hydrogen is above this blue line. So that's basically the situation here. I think maybe the 5-minute period, I think it's over. So I will maybe just show a couple of maybe this one. I like this picture because what we did here was to compare and to find the optimal technology when according to size. So basically this for this case, for this one is the salt electrolyzer when relative sizes is small. And for this case, if we want to build a bigger electrolyzer, in this case, the ALK electrolyzer is better. Of course, when we are above this dotted line, which is the break-even price, which is the NPV. Sorry, it's the NPV of only solar, the only solar system. Whenever we are here, it means that the opportunity cost is positive for hydrogen. Okay.
Wow. So if you have 5 larger than 1, so you actually have a capacity of the electrolyzer that is larger than the PV production. Why would you do that?
But this case is for the self-generation system. You can, even if you have a electrolyzer that double, because this is like behind the meter, let's call it that way. If we have an electrolyzer that double in capacity than the solar system, we can buy the electricity from the system, from the grid, and produce hydrogen. So that's why this tube, for instance, makes sense in this case, because we are buying the electricity from the grid. Okay. Maybe just a couple of things to mention here. Of course, the optimal sizing of the electrolyzer depends on the business model. Of course, the hydrogen price is key here. The electrolyzer, as I mentioned in the last slide, the electrolyzer technology obviously is important to be considered in order to come up with the best design. We are also focusing on energy policy approaches. I didn't mention here one of the works that one of my students is working on. We are also doing some Stackelberg game theory in order to come up with the leader is the government who promotes different incentives for promoting hydrogen, and the leaders are the investors of the followers are the investors of the hydrogen system. So this kind of models are also useful for making or for constructing energy policies as well. So I want to stop here just to.
Can you show us some references do you have that we can read your papers? No.
I don't have it here. I don't have it here.
Fine.
But
Right.
these results are not published yet.
Okay.
We have the paper at the 95% or so. Yeah. So all of these numbers I'm showing here are
Coming up.
yeah, they are not published yet, but the references that we used here, okay, I can add a slide with the references that I used here, and to send you the final version of the presentation.
Fantastic. Diego.
Thank you. Thank you.
Good. Any question here or online?
Thomas, there's a question. Thank you for your response.
Okay, no problem.
So if I understand correctly, you are using a rule-based model.
Yeah.
Finding and parameterizing and then finding.
Yeah.
I was wondering what the utility, what the usefulness is of deriving these analytical expressions of these distributions that you have. If you have this kind of heuristic, well, a rule-based model, you might as well just run all these simulations and then get your answer.
Yeah, that's a very good question. Yeah, but the purpose of all of the work was not obtaining like an approach for operating the system like in real time or something like that, but was mostly designed or employed to come up with this kind of analysis. Sorry, going back like this one, in order to be able to, okay, if we operate the system using this kind of rules, but we will need to have a system designed according to this, and we are providing signals of prices, what should be the prices, yeah, but it's not intended to be a methodology for operating the system in a daily basis.
Yeah, no, I understand that. And then maybe the usefulness then that you have these distributions that you derived in your paper, people can use that as well for simulator.
Oh yeah. But I don't know if they are very particular to the data in that particular location. But the methodology or the approach, of course, is replicable. We employ this optimization model for constructing this, and it worked. We liked the results of this, and yeah, because fitting these bimodal distributions is not that easy. I mean, it's not like we see all of these known distributions have this behavior, right? So maybe with gamma and all of the distributions, you can modify the shape or the scale, but they are mostly with one peak, right? One maximum. So that's why we try to do this. But of the distributions we come up with are, yeah, very particular to the location, to the data that we have, but of course could be shared in order to be employed by other people.
Yeah.
So some of those optimization do you include? Is the electricity price included in the solution? Yeah, so say in the way you have is the size of the electrolyzer versus the PV.
Yeah.
So do you then distinguish when you are beyond one, where they are par, then you have no control of the electricity price. Then it doesn't follow the cost of the PV anymore, because then you are like detached from it. So it's two different price structures, so you could say, because as long as it's a PV, then you have it under control yourself, because it's, you can just cut off and say, I just use the PV. So it follows the cost of the PV, the PV production. As soon as you go beyond the capacity of your PV, the maximum capacity, then you rely on the electricity price that is generated by whatever outside.
Yeah, you don't have control of that. Yeah, yeah, that's true. That's a very good comment. Yeah, and that's we had to in this self-generation system where we can build we can have a big electrolyzer compared to the solar system. That's why in this case, when we use here this expression that we produce hydrogen, if the revenues, let's say that way, the revenues of the hydrogen are above the price of the production value of hydrogen, which is related to hydrogen price and cost of the hydrogen, is greater than electricity price, we produce it. But this is a random expression, right? This is a random variable. So we put the tilde here because the price of electricity has also a tilde that for us, I didn't mention, but for us, it means that the price of electricity is a random variable. So this is a random variable as well. So that's why I employed expectations in all of the analysis, because sometimes electricity price is gonna be very high, and this indicator function gives zero. So it means that don't produce hydrogen because electricity price is gonna be very high. Otherwise, produce it. So that's why it's a random variable.
So the assumption for this, where you change the technology, so I think slide 35, what is the assumption for when you go beyond? So it's 35.
Oh, let's see, maybe this one?
This one, yeah. When you go beyond 5.1, what is then the assumption of the underlying electricity cost? Is it as lot of what is it called?
If I'm an investor and I was going to install a self-generation system with an electrolyzer, I wouldn't choose, for instance, 1.5, because why not do it here? So because this value maybe around 0.5 is much better with the electricity prices that we consider for Colombia, right? So maybe if you say that the electricity prices are lower than the prices I showed, maybe it's much better to produce a lot of hydrogen because electricity price is better. Maybe this figure will shift to the right and would be this maximum would be here. But this is very particular for the electricity prices. For the Colombian electricity prices, I would say if we have a self-generation system, install an electrolyzer around half of the capacity of the solar system, because electricity prices in Colombia are not that low. If they were very low, there is always a good opportunity to buy the electricity and produce hydrogen.
I have one final question. Back to your nice slide 24, that you show the gap between LCOH and BEH. Okay. Do you have also analytical solution for this gap for the red area?
For this red area,
You did all this nice, fitting distribution, blah, blah.
yeah.
But did we have also, closed loop expression for this gap? For opportunity cost?
Not for the opportunity cost, but we haven't tried it.
Okay.
But we have the expressions for the production, for net present value, but not even for these prices. This we have to this NPV function. The NPV function is not linear, so it's not easy to find from here. All of these terms depends on phi.
Yes.
So it's not straightforward to find a closed solution.
All the solution expectation. It's
Yeah.
not risk averse.
Yeah.
And final question: why for gamma distribution you use KS test, Kolmogorov Smirnov?
For which one?
For gamma distribution fitting, while for bimodal you use this optimization. Is there any reason?
Oh, for bimodal is because, as I mentioned, that we didn't find a good distribution that would fit this bimodal behavior.
Okay, but
So-
KS cannot be implemented here. Kolmogorov Smirnov test.
We computed, we did the test for the PDF that we came up with.
Okay.
So
So first you found the distribution,
Yeah.
and then you did the KS
Yeah,
test.
yeah, that was the process. And for price, we could do this, but we still can change our approach, but we prefer to use a well-known distribution because it's not bimodal. So
It's the density on the y-axis, but also it should be below 1.
Yeah.
So maybe also, but the other way.
So again, the question is that the integral of the green
yeah,
area, is it 1 or not?
yeah, it should be 1, but I need to see. We are using R, the software R, for creating the plot of the density. I need to check if this has a particular unit, because what we use is let to know R that plot this, create an histogram using density or using relative frequencies. But in this case, we use density. I will check. I will do the homework and check these the units here, or the integral is 1. But in the optimization is controlled. It's controlled, all that.
We already 7 minutes beyond time, so thank you so much, David.
Thank you. Thank you. Thanks for the attention and for your questions.